Hello everyone, welcome to video 8.6. This is the final video for chapter 8, and we're going to be looking at rational and irrational numbers. This doesn't have maybe quite as much to do with some of the previous sections, so it feels a little disjoint for me, to be totally honest. I feel like this might fit a little bit better with the section on fractions, but hey, it's where it is, so this is where we're going to do it. So yes, let's get started. So as always, we should start off with defining our terms. So by a rational number, what we mean is that we have numbers that can be written as a fraction. Now, this includes things that we obviously think of like 1/2 or 3/4, but it also includes things like zero point 0.5 or 0.75 or zero point 0.3 repeating. Numbers that maybe aren't normally written as fractions in our mind, but they can be written as fractions. I want to point out that the rational numbers also include things like 3. Now, we don't think of writing 3 as a fraction, but it can be written as a fraction. So this can be, here in the definition, is pretty important. Because even though we don't normally write 3 as a fraction, it can be written as a fraction. And so that makes it a rational number. Anything that cannot be written as a fraction is an irrational number, and we're going to save that into the end. We'll talk about the irrational numbers a little bit at the end of this. And it's a little bit of a lazy definition to say that the irrationals are just the things that aren't the rationals. But for our purposes, for what we're going to be doing, it's more than enough. An important characteristic of the rational numbers is that when they are written as decimals, they either terminate, which means that they stop. So zero point 0.1. So that stops, it terminates. Or they repeat with some sort of decimal pattern, like 0.3333, and that 3 repeats. So there's a definite pattern to it. It could be something like 0.121212. So it doesn't have to be just one number that repeats, but there has to be some definite pattern to it. So if you can draw a bar over it and say, well, this is the part that's repeating, then that's what we mean by that. Irrational numbers do neither of these, right? So they don't terminate and they don't repeat any sort of pattern. And so again, we'll talk about that when we get to the end, but just to give you some idea of what characterizes or typifies irrational numbers. So we're going to use division to take a fraction and find its decimal equivalent. So we'll do a couple of examples of this. So one sort of basic example would be to do, say, 1/2. And so we've already talked before that fractions and quotients are effectively the same thing. So this fraction of 1/2 I can write as 1 divided by 2. And we've done problems like this already. 1 divided by 2. And we know that 2 won't go into 1 evenly, so we add the decimal point and the 0. And so now 2 goes into 10 5 times, but we know that that's not a 10. That's 10 tenths. So it goes in 5 tenths of a time. So here's my 10, and then my remainder is 0. So we get a terminating decimal. So we get a remainder of 0, and so it stops. And so we get that 1/2 is the same as 0.5. Not an earth-shattering result, but the point is that we're showing how to use division to find a terminating decimal equivalent. Compare this to, say, 1/3. So now we're going to do 1 divided by 3. So 3 won't go into the 1, so we add the decimal point and the 0 again. 3 goes into 10 3 times with a remainder of 1. Bring down another 0, so now we're moving to the hundredths place. That goes in 3 times. That's a 9 with a remainder of 1. Into the thousands, 3, 9, and we should notice this is going to keep going. And so this is going to be our pattern repeating decimal. So I wanted to do one that was terminating and one that was a repeating pattern, but mechanically it's the same thing. We're still using division, and then once we start doing the division, we should notice that it does one of two things. It either terminates or it repeats a pattern. The pattern's not always obvious. And we may have to do a little bit more, like if you do 1/7, you have to go out to the seventh decimal place before you see that it starts to repeat a pattern. And realistically, you need to go even further than that before you start to see the pattern kind of unfold. So they're not always obvious. They're not always going to be quite so quick and easy. But a lot of the examples that you're probably going to do with your class are going to be ones, 1/4, 1/3, where they terminate very quickly, like 1/2 or 1/4, or where the pattern becomes very obvious, like 1/3 or 2/3, or even 1/6. So now we have to move the other way. If I'm given a terminating decimal, I want to convert this back into a fraction. And I mean, this we've already sort of done this before, so we're just talking about this in a slightly different context. So let's take a decimal like 0.25. So we know that this is our tenths place, and this is our hundredths place. So we know that this is the same as 25 over 100. So this 0.25 is the same as 25 hundredths. Now, we could also, we've talked about this in expanded form, we could say this is 2/10 and then 5/100ths. And then if we do a common denominator, this becomes 20 hundredths and 5 hundredths. So that's 25 hundredths, which is the same answer. So, we have a couple different ways we can think about this, either in this expanded form or just by looking at the smallest decimal place. But either way, we get 25 hundredths. Now, this reduces, this 25 is obviously divisible by 25, and the 100 is divisible by 25. So we can reduce this down to 1/4. And so, this, again, not an earth-shattering result. This is something that I'm going to imagine most of you already know, that 1/4 and 0.25 are the fraction and decimal equivalents to each other. But for a terminating decimal, this is how we're going to convert that terminating decimal back to a fraction. We're going to put it over the place value and then reduce if possible. Now, not all of these are going to reduce. If I take something like 0.11, 0.11, then I know this is 11 hundredths. Well, an 11 is a prime. And so there's no common factors between the 11 and the 100, so this doesn't reduce. This is going to be this fraction in its simplest form. So not all of them will, but if they can, we probably should reduce. Now, repeating decimals into fractions is a little bit more complex of a process. For terminating decimals, we just put it over the smallest place value. This takes a little bit more thought and a little bit more effort. So I'm going to go through this process with you here a couple of times for a couple of different cases, and you'll see how they're different and why I'm going to look at two of them. So I'm going to start with my 0.3 repeating that we've looked at already. Now, I'm going to imagine most of you already know this is 1/3, so the result's not going to be too astounding. But I'm going to set this equal to n. Now, I'm going to multiply that by 10. And so I'm going to get 10 in. And I'm going to write this above for reasons that will be obvious here in a moment. Now, when I do that, that gives me a value to the left of the decimal. I have an integer part now. But more importantly, my decimal parts are the same. And that's really important because what I want to do is now subtract. I want to subtract these. And so this repeating part and this repeating part are going to cancel. And so it's really important that they are the exact same thing, so they cancel. And so when I do 3.3 repeating and I subtract off the 3 repeating, I should just get 3. And on the left-hand side, 10 n's minus 1 n gives me 9 n's. And now we're kind of cheating a little bit because we haven't really talked about solving these algebraic equations. That comes in chapter 9. So we're kind of cheating a little bit, but we can divide both sides by n and get n equals 3/9, which equals 1/3. So my n, which was my repeating 3's, is the same as 1/3. Again, the result we expected, but the process I'm going to imagine new for a lot of people. Um, let's look at another example. Let's take something like 0.1666. And so now this is my n. Well, if I do 10n, then I get 1.6666. And you'll notice the problem here. I can't subtract these because uh, my decimal parts aren't the same. Now, you could, because you're going to get something that terminates, but I found it's easier to go ahead and do 100. And so that's 16.6 repeating. And now all your decimal parts are the same. You can make the 10n and the 1n work. But I said I think that the 100n and the 10n is a little bit more obvious that these decimal parts all cancel. And so now when I subtract these, I get 90n equals 15. So these decimal parts cancel, and then 16 minus 1 gives me 15, and so my n is 15/90ths. And so these are both divisible by 5. So that's 18 and 3. Those are both divisible by 3, and that's 1/6, which I'm going to imagine most of you recognize 0.166 repeating as 1/6. I also want to include into this uh, something like, as a decimal, 0.090909, where the 09 is repeating. So we have a 2-digit block that's repeating. It's the same sort of idea. If I take 10n, then I get 0.909090. And so if I try to subtract these, they're not going to work because they're out of phase. They don't match up. So I'm going to take another power of 10, so I'll do 100n. And so now that moves this decimal 2 places. I get 9.090909. And so now I can see that these match up. And so I can subtract these. I can just go ahead and erase this middle line. And so now I see that these will subtract. These decimal parts cancel. And so I get 99n equals 9. So n equals 9 over 99, or 1/11. So the point for the second example is you may not get something that cancels immediately. So if you do n and then 10 times n, if those decimal parts don't match, you may need to do 100n, even 1,000n, 10,000n, until you get some decimal parts that will cancel, or in the case of 1/6, at least will subtract, leaving you a terminating decimal. It gets a little trickier. Like I said, for students doing this for the first time, I would want to do it where the decimal parts just cancel out completely, and now you're just working with integers in your division. To me, that works out a little bit simpler. So what about irrationals? We mentioned irrationals at the beginning. To be honest, as far as the scope of this class goes, the only thing that you really should probably know is that there are numbers that are irrational, and have a few examples of those. And I think probably one of the most basic ones that most people know is pi. So we've got our 3.141592656, dot, 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 dot. And so this sort of meets our criteria that we talked about earlier. So does this terminate? No. So we can see we've got our dots here. So we know this does not terminate. And this is the one that is a little bit harder to convince students of, and that is probably one of the more interesting aspects of this, is there a pattern? And the answer is no. So it seems strange that this decimal would go on for an infinite amount, and yet there is no discernible pattern, but that's the case. And this pi, because it is irrational, does not have a pattern to it. Or maybe because it doesn't have a pattern, that's what makes it irrational. But either way, there is no pattern to it. And so when you get to, a lot of times, the section on um, circumference and diameter, working with circles. This irrational section might appear before that because you're about to introduce pi. And if students are seeing pi for the first time, it's a lot of really interesting, very sort of seemingly abnormal characteristics. So, you need to introduce irrationals before you get to this. Some other numbers that you might know as irrationals, you may be familiar with this number E 2.71828, which is the base of natural logarithms. You may have seen E before, or something like the square root of 2, 1.4142, also keeps going. It does not terminate, and also does not have a pattern to it. So these are some sort of like basic irrational numbers that you may have run into before. There's a lot more. In fact, there's more irrationals than rationals. I'm not going to go into there's a really interesting proof of why the square root of 2 can't be written as a fraction. I'm not going to do that. You can find it online, or if you want to ask me about it during office hours or outside of class, be more than happy to show it to you. But it's kind of beyond the scope of this class. It's not anything really that you're going to need to be doing in class. But if you're just curious about why that's the case, you can certainly find that proof. So, as a checkpoint, I want you to convert 5/6 into a repeating decimal. So do the division problem to convert the 5/6 into a decimal, and then show how to convert that repeating decimal back into a fraction. Now, you already know the answer is 5/6, so you're converting 5/6 to a decimal, then back to 5/6. But this will give you some practice for doing the division, going from fraction to decimal, and then using that n, 10n, 100n method that we looked at for converting that repeating decimal back into a fraction. So, as always, if you have any questions about this problem or anything else from this video, from this section, by all means, please let me know. All right, thanks.